Hello and welcome. Have you ever flipped a light switch and just paused for a second and wondered, how does that happen? Instantly? Well, today we're going to pull back the curtain on one of the most fundamental yet invisible forces in our modern lives. All right, let's just dive right in and find out how electricity is really made. So let's start with a big question. Where does it actually come from? I mean, yeah, the wall socket. We know that. And before that, a power plant, right? But how? How do they do it? The answer, and this might surprise you, is actually incredibly simple. It all comes down to a kind of magic that happens between two things you probably have lying around your house. And that brings us right here to the magnet and the coil. Seriously, this is the heart of everything. Almost every single watt of power you have ever used in your entire life was generated because of this incredible, surprising connection between a simple magnet and a coil of wire. That's it. That's the secret sauce. It's not about burning something, it's not about some complex chemical reaction, it's just pure physics. The moment you move a magnet near a coil of wire, something amazing happens. You literally create an electric current out of thin air. And here's what's so cool about this. The direction you move the magnet completely changes the electricity. So as you see here, when the north pole of the magnet moves toward the coil, the current flows one way. But the second you pull it back and move it away, poof, the current completely reverses. It's this literal push and pull of energy. So this whole phenomenon, it actually has a name. It's called electromagnetic induction. This is the groundbreaking principle that the legendary Michael Faraday discovered, and it's no exaggeration to say it powers our entire world. All you need is motion. It doesn't matter if the magnet moves or the coil moves, as long as there's motion between them, you get electricity. Simple as that. And the coil is a little, stubborn. This quote kind of gets it why. When you push a magnet toward it, the coil creates a current that makes its own magnetic field to push right back at you. And when you try to pull the magnet away, it creates a field that tries to pull it back in. It's always resisting the change, and that very resistance, that's what we harness as electricity. So what does this mean for us? Well, it means we're in control. If we want more power, the recipe is actually pretty straightforward. You can either use a much stronger magnet, you can move that magnet way faster, or you can just add a whole bunch more loops to your coil of wire. By tweaking just these three little things, we can go from lighting up a tiny little LED to powering an entire city. Okay, but let's be real. Pushing a magnet in and out of a coil all day long isn't exactly a practical way to power a country, is it? And that brings us to the ingenious machine that does all this hard work for us, the generator. And here it is, in its basic form. The electric generator is a brilliant piece of engineering designed for one main purpose, to turn that clunky back and forth motion into a smooth, continuous rotation. So instead of pushing and pulling, we just spin the coil inside the magnetic field. The result? A constant, steady flow of electric current. So what's a generator's real job? It's basically an energy swapping machine. It takes the physical energy of motion, that spinning, that's mechanical energy, and thanks to our old friend electromagnetic induction, it transforms it into the electrical energy that runs pretty much everything in our lives. And this chart is a fantastic picture of what that electricity actually looks like. As that coil makes one single full 360-degree turn, look what happens. The current it produces rises to a peak, drops back down, reverses direction to a negative peak, and then comes right back to zero. This smooth, beautiful wave pattern, that's called alternating current, or AC, and that is exactly the kind of electricity flowing through the walls of your home right now. Okay, so we've got the principle down, and we've got the machine. Now let's scale this thing way, way up. How in the world do you get enough spinning force, enough mechanical energy, to turn a generator that's big enough to power millions of homes? Well, for that, we have to step inside a power plant. And here it is. This is the big secret. This is what's happening inside almost every major power plant on the planet. It doesn't matter if it's a coal plant, a nuclear plant, or a natural gas plant. They are all just incredibly huge, complex, and expensive ways to do one simple thing: spin a turbine. That turbine is connected to a generator, and the generator makes the electricity. The only real difference, the multi-billion-dollar question, is what you use to spin that turbine. For a thermal power plant, the answer is steam. Lots and lots of steam. They burn an energy source, something like coal or natural gas, and use that intense heat to boil massive amounts of water. This creates unbelievably high-pressure steam, which is then shot through pipes to blast against the blades of a turbine, forcing it to spin at incredible speeds. So what about a nuclear plant? Well, believe it or not, it does the exact same thing. It's still just a steam-powered turbine spinning a generator. The only difference is where the heat comes from. Instead of burning fossil fuels, a nuclear plant uses the immense heat released from nuclear fission, the process of splitting atoms, to boil the water and create that all-important steam. So if the final step, that generator, is basically the same, does it really matter how we spin the turbine? Oh, you bet it does. It matters immensely. The choice of energy source is everything, and it comes loaded with some pretty massive trade-offs. The truth is, there is no single perfect source of energy. So let's just look at this quick comparison. On one hand, you have thermal power from fossil fuels. It's generally cheaper to build the power plant up front. But, and it's a huge but, the major downside is the emission of greenhouse gases and other nasty pollutants. Then on the other hand, you have nuclear power. Its huge advantage is that it produces zero greenhouse gases during operation. But it's incredibly expensive to build, and it comes with the very unique and very difficult challenge of what to do with the radioactive waste, not to mention the public concern over safety. Of course, you don't always need steam. What if you could just skip the boiling part altogether? That's exactly what hydroelectric plants do. They use the raw, immense force of falling water stored behind a massive dam to spin the turbine directly. It's just another clever way to get that mechanical rotation needed to power the generator. And that's really what this all boils down to, isn't it? The fundamental physics of making electricity, that elegant dance between a magnet and a coil, is beautifully simple. But the really hard part, the challenge we all face together, is deciding how we create that initial spin. Fossil fuels, nuclear fission, falling water, wind, they all do the same basic job, but each one comes with a very different price tag for our planet and for our future. The science is settled. The choice, well, that's up to us.